Hi, I'm Greg Hinds.
I'm Vannoy.
And I'm Argenis Burgos. Now, we all know adequate wastewater treatment is critical for the protection of public health and the preservation of the environment. But what we may not know is how wastewater is typically treated. Most often, especially in urban areas of the United States, wastewater is usually treated through a mechanized process known as activated sludge. This process is energy intensive and the systems are expensive to operate.
Now, there are alternatives to activated sludge treatment processes, one of which is wastewater stabilization pond systems, also known as lagoon systems. These systems are often more economically feasible for rural and developing communities. Lagoon systems employ gravity to direct the wastewater through a series of ponds. As the water flows through the ponds, natural processes such as gravity settling, microbial metabolism, and UV disinfection treat the wastewater. Lagoon systems are inexpensive to construct, operate, and maintain. However, they do require a lot of space, another reason why they are more common in rural areas.
Pond systems have been shown to reliably meet effluent discharge standards. In fact, many pond systems even meet World Health Organization guidelines for effluent reuse in agriculture. This is one area where pond systems offer potential to recover resources from wastewater. Through effluent reuse in agriculture, nutrients are recovered, taken up by plants, reducing fertilizer costs, and the water is recovered as well. In today's world of increasing water stress and depleting mineral nutrient reservoirs, the recovery of these resources is becoming increasingly important.
Another mode of resource recovery that can be achieved in wastewater pond systems is energy recovery. The first ponds in the series of ponds are often anaerobic ponds. In these ponds, microbes digest the organics in the wastewater in an anaerobic environment and produce biogas that is rich in methane. The methane can be captured and burned to produce heat or converted to electricity using internal combustion engines or steam turbines.
So is resource recovery economical? What does it take to convert an existing system into a full-blown resource recovery facility?
That question takes us up to Belding, Michigan, where a lagoon system has been in operation since 1965. We have been working with Mr. Bill Ribbons, the system operator, to try and answer these questions. We asked Bill what has motivated him to consider options for resource recovery at this lagoon system.
You know, as cost of energy goes up, that would probably be the best advantage to trying to harvest some of the, let's say, the methane off of Pond 1. Basically, it's like a big open septic tank, and it sits there bubbling year round, so I know it's got gas going into the atmosphere that probably could be captured and harvested or used for something. I think probably as cost of energy goes up, if this stuff becomes more valuable, it's worth saving. We could harvest that heat or harvest that energy and use it something that'd probably be worth doing where it didn't used to be.
According to our analysis, which was conducted using operation data provided by Bill, the methane production rate from the anaerobic pond at the Belding system was on the order of 200 cubic meters of methane per day. As the table you see here shows, this is enough methane to produce over 600 kilowatt hours per day of electricity. Even if methane capture and utilization is only feasible during the warm half of the year, over $16,000 worth of electricity can be generated, and greenhouse gas emissions can be reduced by more than 170 metric tons of carbon dioxide equivalents on an annual basis.
Although this would require a large capital investment, the money saved from offsetting the electricity requirements for aeration would accumulate quickly, yielding a relatively short payback period. Effluent reuse for nutrient recovery was also assessed. A significant amount of nutrients could be recovered if the required infrastructure was developed to pump effluent to local farms. This also would be a large investment, but would improve the environmental sustainability of the operation.
In addition to the environmental perks of resource recovery in these treatment systems, effluent reuse has the potential to help these systems meet permitting requirements. Nowadays, with the increasing stringency of effluent standards for discharge to surface waters, there has been an ongoing trend of these systems being replaced by mechanized systems like activated sludge. This results in an overwhelming economic strain in rural communities, which could potentially be avoided by the proper implementation of land application strategies.
That's right. Agricultural eutrophication from excess nutrient loading from surface water is a big problem here in the United States and throughout the world, as is the imbalance in the nitrogen cycle, which is heavily influenced by the Haber-Bosch process for fertilizer production. Nutrient recovery from wastewater through effluent reuse has great potential to aid in alleviating these environmental stressors.
Yes, these are good points. But unfortunately, in the United States, there aren't a lot of locations where wastewater stabilization pond systems have integrated in resource recovery into their operation. This is unfortunate, but hopefully in the future we'll be seeing a bigger push for this. Perhaps the Belding system can even serve as a model for sustainable wastewater management throughout North America.